Dear students, in this video, we will discuss about phase equilibria, and in the first part include number 1, definition of phase components and degree of freedom, then phase rule and the thermodynamic derivation of phase rule, then Clausius-Clapeyron equation, then phase diagram for one component system, that is water and sulfur system. Now let us discuss what is phase. Suppose we are considering a water system. If we decrease the temperature up to 0 degrees centigrade, then water liquid, it will convert it to ice. Similarly, if we increase the temperature from room temperature to 100 degrees centigrade, then we will see that water liquid will be converted to water vapor. So water exists in 3 phases. One is solid, one is liquid water, and one is water vapor. Hence, a phase is a homogeneous and physically distinct portion, that is homogeneous and physically distinct portion. Ice is distinct from water, water is distinct from water vapor, and they are mechanically separable. They can be separated. Ice can be separated from water, water can be separated from water vapor. Similarly, in oil and water system, it exists in 2 phases. One is oil, one is water. In a gaseous mixture, there is only one phase, that is gas. Next is what is component. Now, if we consider water, ice and water vapor system, then it is only one component system. That is the smallest number of independently variable constituent through which the composition of each phase can be expressed either directly or in the form of chemical equation. So water, ice and water vapor system, in all the cases the composition can be expressed in water. So it is only one component system. And similarly, rhombic, monoclinic, liquid and sulfur vapor. Sulfur exists in 4 phases: sulfur rhombic, sulfur monoclinic, sulfur liquid and sulfur vapor. In all the cases, the composition can be explained from sulfur itself. Hence, it is a one component system. Similarly, if we see calcium carbonate, which is in equilibrium with calcium oxide solid and carbon dioxide gas, it is a 2 component system because calcium carbonate can be expressed from calcium oxide and carbon dioxide. Similarly, dissociation of ammonium chloride, phosphorus pentachloride, these are the examples where the smallest numbers are, it may be 2, it may be 3. In phosphorus pentachloride, at low temperature it is a 2 component system, and at high temperature it is only 1 component system, that is the gaseous form. Hence, the component is the smallest numbers of constituent through which the composition can be varied. Next is degree of freedom. To define a system in equilibrium completely, we need 3 variables, that is temperature, pressure or composition. The degree of freedom is the minimum number of the independent variables which define a system completely. For example, the equilibrium between water and water vapors, only one independent variable is required, that may be pressure, that may be temperature. Hence, the degree of variable is 1. Similarly, in equilibrium between water, ice and water vapor, we don't have any independent variables. Hence, here the degree of freedom is 0 because pressure, temperature cannot define the equilibrium between ice, water and water vapor. For a gaseous system, both temperature and pressure are required to define the system. Hence, the degree of freedom is 2 in gaseous system. What is phase rule now? The phase rule is for a closed system and in a heterogeneous system, degree of freedom F is equal to component minus phase plus of 2. For example, if an equilibrium between carbon solid to carbon dioxide gas and carbon monoxide gas and oxygen gas. Here phases are 2, components carbon and oxygen, then the degree of freedom is 2. Similarly, I2, iodine, solid, chloroform and water system, the phase is 3, component 3, degree of freedom is 2. Similarly, ammonium chloride is solid, ammonia gas and HCl gas, these are in equilibrium, then degree of freedom is 1. Now, thermodynamic derivation of phase rule. To define a phase rule thermodynamically, we need to consider the chemical potential of different components, suppose 1, 2, 3 to C, in different phases, suppose A phase, B phase, C phase up to P phase. So the chemical potentials are, it will be mu1 for A phase, mu2 for A phase, mu C for A phase for different components. Mu1 for B phase, mu1 for B phase, mu C for B phase, that is mu2. Similarly, mu1 for C phase, mu2 for C phase, mu C, component number C for C phase, up to mu1 P, mu2 P, up to mu C for P phases. So these are the chemical potentials for different components for different phases. Now, dn moles of the components are transferred in equilibrium condition from one phase to another. Suppose dn moles of the phases are transferred, then since these are in equilibrium condition, so numbers of moles in each component in each phase will be changed equally. So the change will be 0. So dn1 in A phase, dn1 in B phase, dn1 in C phase up to dn1 in P phase, dn2 in A phase, dn2 in B phase, dn2 in C phase up to dn2 in P phase, dnc in A phase, dnc in B phase, dnc in C phase up to dnc in P phase, it will be 0. This is equation number 1. Now from Gibbs Duhem equation, it is a thermodynamic equation that the Gibbs free energy change is equal to summation of multiplication of the chemical potential and change in the number of moles, total number of moles, it's a sum, is equal to 0. That means mu1 dn1 for A phase, mu1 dn1 for B phase up to mu1 dn1 for P phase, mu2 dn2 for A phase, mu2 dn2 for B phase, mu2 dn2 for P phase, mu c dnc for A phase, mu c dnc for B phase up to mu c dnc for P phase. This is the summation is equal to 0. This is equation number 2. Now, if we multiply equation 1 by constant lambda, lambda 1 for this, lambda 2 for this, lambda 3 for this, lambda n for this, then we will get this one, lambda 1 dn1a, lambda 2 dn2a, lambda c dnca for P phase is equal to 0. This is multiplying equation 1 by lambda. So from 2 and 3, this is equation number 3. And from equation number 2, what we are getting, mu1 dn1 up to mu c dnc equal to 0. So mu1 d1 is also 0. So lambda 1 d1 is also equal to 0. That means what? Summation, by summing 2 and 3, then we will get that mu1a is equal to minus lambda 1, mu1b is equal to minus lambda 1, mu1b is equal to minus lambda 1. That means in all the components, in all the phases, the chemical potential is equal to, the chemical potential is equal. So mu1a is equal to mu2, mu1b equal to mu1p. All the phases, the chemical potentials are equal. For mu2a, mu2b, mu2p, mu ca, mu cb, mu cp. That means the chemical potentials are equal for all the components in that phase P. So this is the derivation of, this is the equation for phase equilibrium. Now, to calculate degree of freedom, that means the number of variables, we need to calculate the total number of variables. Suppose for a C component system and for one phase, if one component is fixed, then the rest of C minus 1 component will be variable. Suppose we are considering only one component is fixed, then the rest C minus 1 component will be variable. So that will be for one phase. Now for P phases, suppose we have P phases, then the total number of compositions variables will be P into C minus 1. So C minus 1 will be for one phase and P into C minus 1 will be for P phases, that is the numbers of variables. Now along with P into C minus 1, we have to add two more variables, that is pressure and temperature. Hence total numbers of variables will be P into C minus of 1 plus of 2. This is coming from pressure and temperature. Now the chemical potentials for the component 1 of the phases is defined. The chemical potentials for the P minus 1 phases are constant. So we are considering the equilibrium changes of one phases. Then P minus 1 phases, composition of P minus 1 phases will be constant. So composition of only one phase is varied and P minus 1 composition will be constant. Hence P minus 1 is constant. Now concentration of the components for all the C, the compositions, this is for only one component. For the C component, it will be C into P minus 1. Hence, C into P minus 1 numbers will be constant for a phase transition. Hence, the total numbers of variables will be, that means numbers of degree of freedom will be total numbers of variables minus fixed value. Then we will get the numbers of variables. So it will be P into C minus 1 plus 2 minus C into P minus 1. This is coming from that is one phase. P minus 1 will be constant. The total composition will be C into P minus 1. And it is coming from total numbers of variables. There is composition 1 is fixed, C minus 1 is variable. So total phase is P. That's why we are multiplying P into C minus 1. And plus 2 is the temperature and pressure. So it will be P into C minus 1 plus 2 minus C into P minus 1 equal to C minus P plus of 2. That is the phase rule. Now phase diagram and Clapeyron equation. Already we know that we need three variables, pressure, temperature and composition, to define a heterogeneous equilibrium. So the effect of changes of temperature or pressure or composition on the changes of phase will be expressed by a graphical representation, that is the phase diagram, which include the change of the equilibrium, change of the phases. So when there are only two variables are there, that may be pressure temperature or pressure concentration or temperature concentration, then we will give the rectangular coordinate, that is x-axis and y-axis, and in that case time is kept constant. Basically we will use only the pressure and temperature, and in that case concentration will be remain constant. Now the effect of pressure and temperature of transition from one phase to another of a substance is governed by Clapeyron equation, and this is dP by dt is equal to del H by T del V is equal to del S by del V. Del H by T is equal to del S entropy, and there is del H enthalpy, and T is the transition temperature. That is from solid to liquid, it will be boiling, melting point. Liquid to vapor, it will be boiling point. Solid to vapor, sublimation point, like that. So the plot of T and P and T would reveal the conditions of equilibrium between the two phases. And if in the transition from liquid to vapor, dP by dt is positive because del S entropy is also positive, volume is also positive. Similarly, from transition from solid to vapor, del S is positive, del V is positive. So dP by dt is positive. Transition from solid to liquid, del S is positive, but del V is either positive or negative. Hence, dP by dt may be either positive or negative. So, if we consider in one component system, suppose water, this is the phase diagram for water system, where this BO is the sublimation curve, OA is the vapor pressure curve, and OC is the melting point curve. Here BOC is the area of ice, COA is the area of water, and BOA is the area of water vapor. A graph is plotted with pressure and temperature. Obviously these are not in scale. So right hand side of BO, it is ice, this is water vapor, and left hand side of BO is the ice. Similarly, COA is the water, AOB is the water vapor. And this O is the triple point where the degree of freedom is 0, where all the three phases are in equilibrium, they are coexisting. Hence, increasing temperature, increasing pressure, it is the sublimation curve. Increasing pressure, increasing temperature, it is the vapor pressure curve. And decreasing temperature, increasing pressure, that is melting point curve. Ice is converted to water, water is converted to ice. So this is the summarized table where regions, phase in equilibrium, number of phases, degree of freedoms are there. These are the areas, these are curves, these are points. Similarly, if we see the sulfur system, sulfur exists in 4 phases. One is rhombic sulfur, one is monoclinic sulfur. These are solid form, this is liquid sulfur, and this is vapor sulfur. So this is the phase diagram where pressure is in y-axis and temperature is in x-axis. So this is the sulfur rhombic to sulfur vapor curve, sulfur monoclinic to sulfur vapor curve, sulfur liquid to sulfur vapor curve, then sulfur rhombic to sulfur monoclinic transition curve, and this is the sulfur monoclinic to sulfur liquid vapor curve. And here this is the phase diagram for sulfur system, where beyond this it is the vapor sulfur, this is the rhombic, solid rhombic, this is the solid rhombic, this is the monoclinic, this is the phase equilibrium between rhombic and monoclinic, this is the equilibrium between monoclinic and liquid, this curve is the equilibrium curve between liquid and vapor, this curve is the equilibrium curve between solid monoclinic and vapor sulfur. One more point I forgot to mention, that where the in water system where the pressure is 1 atmosphere, then the temperature is 100 degree, this is the boiling point, and where pressure is 1 atmosphere and temperature is 0 degree, that is the melting point. In melting point curve, this is in the boiling point curve. Similarly, sulfur system also, here 444 degrees centigrade is the boiling point, this is 1 atmosphere pressure, where liquid is converted to vapor sulfur, this is the boiling. So this is the summarized tabular form of sulfur system. These are the areas, phases, number of phase, and degree of freedom. These are curves, phases, number of phase, degree of freedom, and these are triple point, these are metastable equilibrium. So what is metastable equilibrium actually? Metastable equilibrium means if we extend the DC curve here up to F, if we extend the AB curve up to F, if we extend the ZE curve, means this E point up to F, then we will get a metastable equilibrium. That's all for today. Thank you.